this is the last problem we worked. We were given a concentration of a weak acid, 0.100 molar of hydrocyanic acid. You're given the Ka. If I don't give you the Ka, I will provide you with the table so you can look up what the Ka is. And you are asked to find the hydronium ion concentration. So what we're asking is how much of this shifts to the right. We know initially we have 0.1, and then it's going to shift by a factor of x, and that factor of x happens to be equal to the hydronium ion concentration here. And from there we can get the pH. We also made an assumption that the percent dissociation of the initial acid is very small. Based on the fact that our equilibrium constant is very small, we know there's not a whole lot that shifts to the right. We also had a rather large initial concentration of the acid, so that percent, which is hydronium ion divided by the initial concentration times 100, was 0.007%, and as long as that's less than 5%, we can actually argue that x is essentially 0 in this case, and so we can make it go away, right? So with respect to the initial concentration, then solve for x and obtain the hydronium ion concentration that way. So the relationship between the hydronium ion concentration and the initial concentration of the acid can be calculated. We call that percent ionization. It's shown here. This is true for any acid, and it's actually, as we will see, also true for bases. Bases also have a percent dissociation to form hydroxide, and so it's going to be very similar. And it also is true that the larger the the acid concentration is, the smaller the percent dissociation. Okay, so this is down here. This means that the increase in hydronium ion concentration is slower than that of the acid. Okay, so now it's your turn. This is essentially the same idea. You're given a different acid, you're given a different concentration, and you're given the Ka for that. And so I've given you the ice table. All you have to do is fill it out and solve for x, and don't forget to do percent ionization so that you can make your algebra a little bit easier. And if you're not sure if you did it right and you don't have a solution handy, come see me during my office hours and I'll help you out with that. So here's another example of a weak acid solution, and this time we're asked to find the pH. Let's just simply one step further. We can just use this equation. I'm going to put the ice table underneath. I think I should have enough space for here, but my initial concentration is 0.100 m, and this is of course 0 and 0 before it shifts. So you know what this means is you took either solid or liquid or gas, whatever this is, and you dissolved it in enough. You took 0.1 moles and you dissolved it in enough water to make it exactly 1 liter, and so that will then shift by a factor of x, so minus x. This goes up by x, this goes up by x, and then at the initial concentration is simply 0.00 minus x, and then x and x. And if I plug that into the equilibrium expression, which is Ka, but we know, of course, know what the number is, 1.1 times 10 to the minus 2 is then equal to x squared divided by 0.100 minus x. I'm going to assume, and we'll see if that's true because we'll do percent ionization, that that's negligible, but this is rather large, so maybe not. And then if I solve for x, it's x squared is going to be equal to 1.1 times 10 to the minus 2 times 0.100. If I take the square root of both sides, this goes away, and then this is of course a 0, and if I solve that for x, x is going to be equal to 0.033, and when I calculate percent dissociation, it's 0.033 divided by 0.100 times 100, which is unfortunately 33%, which is much, much, much larger. So we cannot make this assumption. We have to use the quadratic equation. I suggest that you do this yourself. And once you've done that, you can come back to this slide and make sure that you did it right here. The problem is all worked out. And so for x, of course, we get two answers. One is negative, one is positive. And then all you have to do is take the negative log of 0.028 to get to the pH, which is the question here. All right, so another example. We have 0.100 molar solution of a weak acid. It's generic. We don't know which one it is, so we can't look up the Ka, but we're asked to calculate the Pa, and instead we're given the pH. So we use the same concept. We understand we have an acid that is weak, and that's important, so we know we have an equilibrium. It's going to break into H plus and A minus. And we set up an ice table. We initially have 0.100 and then 0 and 0. And instead of calculating for x, we can determine x based on the pH. So all we need to do is take the inverse negative log of 4.25, and that's going to give me the H plus concentration, which normally would be x. And so that is 5.6 times 10 to the minus 5. So then we know it goes down by that factor, 1.6 times 10 to the minus 5. It goes up. So here it's plus 5.6 times 10 to the minus 5. And then this is a little skewed because the number is so large and I didn't leave enough space. And then at equilibrium we have 0.100 minus 5.6 times 10 to the minus 5. So I really should have made more room here. And then plus 5.6 times 10 to the minus 5, which is H plus. And then also, again, 5.6 times 10 to the minus 5. I plug this into the Ka, which is what we want to calculate. So that would be 5.6 times 10 to the minus 5 times that. So I square that, divided by 0.100 minus 5.6 times 10 to the minus, and this is a 5. This looks like a 3 here. It is what we calculated from the pH. That's what x is, or we don't have x here. I guess our x is Ka. And then from that you get an equilibrium constant that's 3.1 times 10 to the minus 8. Okay. Your turn, right? Anyway, this is the solution. And then you can work this exact same method on your own for a pH of 3.25 and an initial concentration of 0.15, right? So 0.175 goes into here, and then whatever the inverse negative log is goes in here. You can do this, have some fun. Wrong direction. So let's find percent ionization for an acid. This is nitrous acid, HNO3. I don't have the Ka here, but I will have to give it to you, or you cannot work this problem. So we set up an ice table and initial concentration of 2.5. 0, 0, this goes down by a factor of x, goes up by a factor of x, and then this is 2.5 minus x, and plus x, and plus x, Ka, which as I said I have to provide in this case, or you look it up. I'm probably going to give you the Ka for nitrous acid is, where did it go? 4.6 times 10 to the minus 4. So that's Ka, so I can plug this in. 4.6 times 10 to the minus 4 equals x squared divided by 2.5 minus x, assuming that this is relatively small or negligible in comparison to 2.5, a very, very large concentration. Solving for x means I have the square root of the Ka, 4.6 times 10 to the minus 4 times the initial concentration, which is 2.5. If I do that, I get a concentration of 0.034 mole. It asks us for percent ionization, so all I have to do is take that 0.034 and divide it by the initial concentration, which is 2.5, and multiply. If you wish, you can put m and m in. It cancels because we're doing a percent times 100, which is equal to 1.4%. That's all it's asking us to do. If this was larger, we might have to do the quadratic equation, because then that percentage is going to be different. If x is larger than, rather large, then it's going to have an impact on that 2.5. All right, so let's take a break, and when we come back, we're going to work more ice tables. What do you know?